So good Thursday afternoon. Welcome to lecture 10, Maths for Construction. When we did lecture 9, we did the basics of coordinate geometry. All these things here you would have covered in CSEC mathematics when you were a teenager, right? There's nothing here that is not on the CSEC syllabus, right? The caliber of the question though involves maybe working with SIDS. And SIDS is a higher level technique, which we did on lecture 8, I believe. Where is it? So I kind of have to go through these things and make sure you understand how to deal with it. All this stuff it SIDS here is very good to know, complete any square, a perfect square, difference of two squares, min max values. Again, all these things are on the CSEC syllabus, and I gave you the chapters in the book to study for that, for the algebra foundations, right? Moving forward here, where coordinate geometry, there's a natural progression into calculus, okay? Calculus is on the syllabus here. You see learning outcome trees about calculus, and it's a very big topic, and it tends to get a little complicated. Right? There's a lot of material to cover. That's why I give you the textbook chapters to cover for calculus. As soon as you finish algebra, you could jump straight to calculus. Right? Graphs might help you a little bit, right? Where you jump straight to calculus. So we're doing from 42. Now, I mean, I'm not going to rewrite these notes from the textbook. We all have the textbook. I could just go through the textbook and show you which parts to focus on, right? The lectures that we would be having, where I would be typing notes here, would be solving questions, right? Really giving you questions and solving. I don't want to rewrite all the notes already in the textbook. To me, that's kind of wasting time. Class is really to focus on the parts that are important and do questions, do hard questions. So the introduction to differentiation. So they say here calculus is a branch of mathematics dealing with varying functions that vary. So one time is not really about straight lines, okay? It's about curves, because curves, the value of y varies kind of unpredictably sometimes, right? We have roughly two branches. We have the differential and we have the integral, right? The differential calculus or differentiation talks about finding the gradient function. That's a big thing in differential calculus. We're given a function, you want to find a gradient function, right? In integration, you're given the gradient function and you're asked to find the original function. What these things are, you probably don't understand it, right? So we have the functional notation here. Everybody familiar with y equals something, right? F of x equals some function here. Make this a little bit bigger. There's a functional notation here, and we use this notation to find a y value based on an x value. So given an x value, you plug it into the formula and you get the corresponding y value. So y equals f of x, right? That's the same as saying y is a function of x, right? So when we say things like y equals f of x, f is the function and f of x means a function of x. So x is the independent variable and y is the dependent variable. Y is a function of x. That's really what the statement is here. And sometimes the rule of the function, right? Sometimes the rule of the function. The rule of the function is it's a You're given an algorithm how to find y given a value of x. Okay. So sometimes we know the rule to follow. Well, sometimes it's not just rule, sometimes it's a bunch of rules to find the y value given an x value. Okay, so you might say things like say y equals f of x and f of x equals something, some polynomial or something. So say 2x squared minus 3x plus 5, right? This is the rule here. Sometimes you know the rule. It's called the closed form of the rule. This says how to find the y value given an x value. And we have notation for that, right? So we could say when x equals 3, y equals f of 3. That's the nice thing about this notation here. So given our x value, we could find our y value. We just plug it into the formula, you know, B and A, the rule they give you. So wherever you see x, you just put 3, right? So f of 3, you put, wherever you see x, you put 3. So, I mean, it's broad mass, right? 3 3s are 9, 9 2s are 18, minus 3 3s are 9, plus 5. That's 14, I believe, right? So we say things like 3, 14 is a point on the curve right? Because when x is 3, y is 14. The y coordinate is 14 and the x coordinate is 3. So we said 3, 14 is a point on the curve. Okay. I have different kinds of notation that you could use, but I'm trying to stick to notations that are easy to write on your computer. Okay. But that's what it's saying here with this function notation. Given an x value, we could find a y value, right? So you see, if f of x equals this, find these values. F of 0, f of 3, f of minus 1. They're asking you to find y values. They're giving you the x value. They give you 0. F of 0 is the y value corresponding to x equals 0. F of 3 is the value of y when x is 3. So that's a different point, right? And you know, you just substitute and you find these things here. This is the function notation that they're trying to show you, right? But you see, they come quickly and swiftly to the idea of the gradient of a curve. Now, not gradient of a line, because that's boring. Given a straight line graph, it's easy to find the gradient. Just find 2 points, and we even have a formula for the gradient, as we saw up here in lecture 9. If you have a straight line, this is the gradient. It's the first thing you learn in finding anything about a straight line. Knowing 2 points in a straight line, how to use it to find the gradient. And the gradient is a measure of how steep the line is, right? The higher the gradient is, the more steep it is. Think of you're climbing a hill. A very large gradient means a very steep hill that, you know, not fun to climb by itself. You might need equipment, right? But a very small gradient is a small incline that might be easy to just walk and step up, you know. So the gradient of a straight line is a kind of boring thing because it's very easy to find. But the gradient of a curve changes is defined as the gradient of the tangent at a point. And that's the thing. With a curve, the gradient changes all the time, man, because the tangent line changing all the time, right? You draw a curve, you see here this diagram here, figure 42.1. This is a point P. A tangent to a curve at a point is a line, a straight line that only touches the curve at the point. Okay? If you take a point slightly higher up here, you get a different tangent and therefore a different slope and therefore a different gradient. So the gradient is changing. How is the gradient changing? That's what we want to know. We know the gradient changing with a curve. The gradient different all over the place. It's not like a straight line because the tangent at a point, the slope of it changes all the time. So, you know, we want to find what the gradient is at a point. So here, look at the talking here. We have coordinates here to find the gradient of the tangent. So it's just the slope. So you see here now, figure 42.2, right? You have a curve. We have 2 points on the curve, right? Each point has coordinates x1, y1, x2, y2, and well, y1 is f of x1 and y2 is f of x2, okay? The idea is if you the length of this tangent here, AB, well, it's not tangent, there's just a chord, is what we call a chord. A straight line joining 2 points on an arc is called a chord, right? So AB is a chord. The idea is the gradient of AB approaches the gradient of the tangent at A as the length of the line shrinks, as B gets closer and closer to A. And that's what this diagram here is showing you. If B is quite up here, you see up here, B is quite up here. You see the chord AB has a gradient, okay, that we could find. But as B gets closer, say it reaches point C, the gradient of the chord changes, all right? As C gets closer to A, say point D, that gradient AD changes. The closer the point gets to A, the gradient of that chord from A to the point gets closer and closer to the gradient at the point A. That's the idea. So it's a limiting process, right? So look here, finding gradient of chord AB, right? Using 2 points, it says 4. Then define the gradient of AC, that's 3. Then define AD, 2.5, right? Shrinking it smaller and smaller, smaller. Eventually, you know, you're going to get something real close to 2. Okay, the gradient at the point A. Right, this is y equals x squared, right? So the gradient is actually 2 at point A. But it's a limiting process here. We're trying to estimate the gradient using these limiting processes and doing calculations here. This is not always feasible, right? So you see here, they say the limiting value of the gradient for chord AB when B coincides with A is what the gradient of the tangent at A will be, okay? And that limiting process, they have different notations for it now. So we have differentiation from first principles here, where we have a curve and we have 2 points A and B, and we want to find the gradient of the chord AB, and that's what we call delta y delta x. Why this strange notation delta? What's this delta symbol here? That's the 4th letter in the Greek alphabet, commonly used to mean a change in something, right? So if time changes, we say delta t, t being time. So delta is a symbol used to signify in mathematics that there's a change in something. So delta y means the change in y. Delta x means the change in x. So here's the gradient of chord AB, right, is delta y, which is vertical, and delta x horizontal. Where's delta y? From the diagram, where's the coordinator B? If the coordinator A is x, the x coordinator A is x, then the x coordinator B is x plus delta x. And if the y coordinate of A is f of x, the y coordinator B is f of x plus delta x, because that's the x coordinator B, right? So if you do some simple differences here, what we get up here is that delta y delta x is this expression here, this first principle, right? They say as delta x approaches 0, this would actually approach the true gradient, right? Which we write it as dy dx. So what they say, the limit of this fraction as delta x tends to 0 is the limit of this fraction here, fx plus delta x minus f of x over delta x, right? And the limit as delta x tends to 0. Now you tell yourself, well, just substitute 0 for delta x, right? But yeah, that wouldn't work. Okay. Anything over 0 is probably a large number, so you don't just want to substitute. And this is why differentiation spawned the idea of limits, which is what calculus really rests on top of, the analysis, right? That analysis of limiting processes. That is what calculus is built on, but you all actually don't have to know it. Engineers use calculus like a toolbox, like how you just open a toolbox, grab a wrench and use the wrench. You don't care who made the wrench or how the wrench works, you just know it solves the problem for you. That's how engineers tend to use calculus. So we don't really find limits, okay? But this is the functional notation, is this complicated thing here that looking like, looking kind of difficult, right? But the limit of delta y delta x is what we call dy dx. And dy dx is a function, which we call a gradient function, okay? So they show you here differentiation for first principles with f of x equals x squared. You have to find the limit of this fraction here. So f of x plus delta x is x plus delta x all squared, because that's what f of x is. F of x is x squared. So anything you find in any x value you substitute in, you just square it to find the y value. If you expand this out, you'll get this expression here. So the limit as delta x tends to 0 is this expression up here divided by delta x, which is all of this here, which is this here, right? Now you see the limit as delta x tends to 0 of 2x plus delta x. If delta x tends to 0, you'll end up with 2x, okay? And that's really what dy dx is, or what we call f prime x. Again, more notation, right? F of x is the function, f prime x is a gradient function, and that's what we want to find. We want to find a gradient function given a function. But we don't always want to do it by first principles, because you have to learn a lot of mathematics to deal with even simple functions like sine x and cosine x. It's very hard to differentiate these things from first principles. You have to learn a lot of trigonometry in order to deal with that. But you see in the notation here, dy dx equals f prime x. That's the gradient function. Okay, so gradient function. What is the gradient function? Given a function f of x, the gradient function is also a function of x, right? And is given by dy dx. All right. So this is two different notation. One, if you tell me you want to find dy dx, I know you mean the gradient function. If you tell me f prime x, I know it's a gradient function you're talking about. It's two different ways of saying the same thing. And it's because the textbook using it. That's why I'm showing it to you. If the textbook didn't use it, I'll probably just show you one, which is dy dx, right? But they're talking about f prime x. You say f prime x is 6x squared here, right? So we need to know about it when you see it, right? So we wouldn't go through the first principles because that's kind of long. We want to find the gradient function of a simple polynomial, ax to the power n. And they give this rule here. If your y equals ax to the n dy dx, there's actually a formula for it, right? And you know in mathematics, we love formulas, right? So so some popular gradient functions. And there's a way of doing it, right? So here they say if y is ax to the n, then dy dx is all of that, right? So we could say that too. But there's a different way to write it. So what is this? What is this ddx thing about here? Right? There's another notation. They don't have it here really, but that is a notation we would use a lot. Instead of saying y is the function. So this is the function here, and this ddx on the outside, that is called the differential, the first differential operator. Okay. So let me talk about that first. The first differential operator. So the first differential operator is applied to a function and it generates another function, right? So you have to spend some time understanding the terminology behind this thing, right? You had to spend a little bit, but it's all right. You gotta get used to it. So ddx is the first differential operator. And when you apply it to some function f of x, what you end up getting is f prime x, right? So the operator, it's an operator, meaning it's like a function in itself. It is a special kind of function, right? What it does, it operates on a function and gives you another function. It is a transformation. You see, like our function operates on x and gives you a y value, like up here. F is a function, right? F of x. F is a function of x. You see how f takes a value 3 and maps it to 14, right? A differential operator is also a function, but it operates on a function. It operates on a number. When you give it a function, it gives you back another function. Instead of giving it a number and it will give you another number, you give it a function, I will give you another function, right? it means differentiate one time, right? So what you could also have is the same thing. If you differentiate with respect to x, y, you will get dy dx. That's where the terminology comes from. Dy dx is not a fraction, is a function, right? So this means differentiate with respect to x. The above statement means differentiate y with respect to x. Okay. Okay, so dy dx is not a fraction. It is a function and it is obtained from y, right? Or f of x by applying the operator to the function f of x. Okay. So this terminology will be a little different for you guys to grasp, okay? The gradient function dy dx, that is a function. It is obtained from the original function f of x, you see, by applying the first differential operator. And what is a differential operator? It's a function that operates on other functions. It's a special kind of function, right? So when we apply d dx to a function, we get another function, and the output is the gradient function. What is the gradient function? What really is it? It's a function that given a value x, we could find the gradient, okay? So using the gradient function, we can find the gradient at a point given the value of x without finding any gradients or tangent lines. Remember that's what I was doing before? Those drawing a line and estimating. You see here? Those drawing a line between 2 points and making it closer and closer and closer and trying to access the value of what the gradient would be. That's not very practical. So what we want, what if we could find a function that given a value of x, we could find a gradient? That's what you call a gradient function. The original function given a value of x, we find the value of y. So we give it a value of x and it tells us what the y value is. The gradient function is different. When you give it an x value, it doesn't tell you what y is. It tells you what the gradient is at that point. That's what we want to find, okay? It turns out that you could find a gradient function easily for simple functions. And it means you have to apply the differential operator to the function, okay? So this is a popular gradient function here, as we saw. Where's the rule? Where did it go? right? An x to the power n minus 1, right? So you see here, they did some examples. If y is 3x squared, what is dy dx? What is the gradient function? To find the gradient function, we differentiate with respect to x the entire function itself, right? So you could actually see that with a work example here. Let's say example 1. So y is equal to, say, 3x squared. That's what they said there. Okay. So they say find a gradient at x equal, let me say 2, when x is 2. Where's the gradient when x is 2? That's what I want to know. Now I could draw the curve on graph paper, find the point when x is 2. When x is 2, y is 2 2s are 4, 4 3s are 12, y is 12. I could find a point on graph paper, draw a tangent that cuts the curve at only that point. And there's some guesswork in that, because your tangent might be slightly shifted from mine. So both are we going to find different answers if we do this graphically on graph paper, right? Because you had to guess, you had to eyeball it, you had to use your judgment and be like, that line looked like it's touching the curve at only one point. Is never really get the right thing, right? But you could guess. The idea behind calculus, differential calculus, is we don't need to guess. We just find the gradient function using this rule up here, right? So if y is that, so why is this? Let's find the gradient function, okay? So dy dx, how do you find that? You have to differentiate y with respect to x. So we have to apply the first differential operator, d dx. We need to apply that to y. Right? So when you find d dx of y, that's why they get the dy dx. What mathematicians did to shorten the notation, they just put the y in the numerator and call it dy dx. That's what I had here, right? That's where dy dx comes from. D dx is the operator, and when we apply it to a function y, we get another function dy dx. They kind of confuse the notation a little bit by combining it and just putting the y up here. But dy dx is not the same as d dx. dy dx is a function. D dx is also a function, but d dx is the differential operator. When we apply it to y, we get a new function, dy dx. So what is this? What is, we have to substitute for y now, d dx at 3x squared. Okay, what does the rule say? Okay, the rule says if you have ax to the power n, this is ax to the power n. You leave the a on the outside here, but you see this n, multiply a by n. So this is, I'll have the 3, but I'll have the 2 because that's what n is, x to the power, and this is 2 minus 1. Group of brackets around that. Yeah. So what is this? This is 6x to the power. Well, 2 minus 1 is 1. 6x to the power 1. They just call that 6x, right? So that's the gradient function. This is the gradient function. But what did they ask? Find the gradient at x equals 2. So now we have to say dy dx, right? This is why they are the notation f prime of x, right? So I could say let just introduce the concept because they never give us that, right? I say let f of x equal y, okay? So I introduce the concept of fx because the only question they just give me y. So I said let f of x be this thing. Then f prime of x, f prime of x f prime of x is dy dx. So if f of x is y, f prime of x is dy dx. It means that's the gradient function. Remember, both is the same thing, right? Up here, f prime of x is dy dx. See it here? It's just two ways of saying the same thing. However, f prime of x is an easier way to write because it's function notation. So what they wanted here, they wanted f prime of 2. So I could come and say f prime of 2 because they wanted when x equals 2, right? You substitute 2 into the gradient function. So this is 6 by 2. Which is 12. So for the curve y equals 3x squared, the gradient of x equals 2 is 12. Right? That's not the y value. Y value is 12. Right? But for different values of x, you will have different gradients. We're not so interested in finding any y value. To find a y value, we just use f of x. But to find a gradient, we use the gradient function. And you find a gradient function by differentiating with respect to x. That's what this here, we differentiate with respect to x. That's what you have to do, right? So this is what they're doing here. They say y equals 3x where dy dx is 6x, right? All these things is what I just did, okay? And now using the general rule, they say, well, find the gradients of these functions here. And it's just to follow through with your rules of indices and polynomials, right? So that's what the examples here are showing you. Just a lot of examples for how to find the gradient. And it turns out gradient, you know, the first differential operator is a linear operator, right? Let me write that up here. This operator is a linear. What does it mean when we say a linear operator? Okay, this is what I want to talk about now. What do I mean by a linear operator? Suppose A and B are constants. And f of x g of x are both different functions of x, right? So A and B are constants. A, F, X, G. Okay. If I differentiate with respect to x, this expression here, right? then this is what this is what you end up with. You could actually take out the constants, right? So you'll get A on the outside and B on the outside because it's constants. And inside of here now, you'll just have the f of x and here you will have the g of x, which is a f prime of x. Okay, this is what a linear operator means. A linear operator means the image of a sum is a sum of images. Okay, so here we're trying to differentiate two separate functions, and each function f of x and g of x have a number in front of it, a constant a and b. Let me say non-zero to make sure, right? So it's non-zero constant. If you differentiate across the sum, the operator distributes across the sum, you see here? And the constant doesn't affect things. You could actually put the constant outside in front of the operator. So you differentiate f of x, put the a in front of it, and you differentiate g of x, put the b in front of it. Now we know the derivative of f of x is f prime x, and you know the derivative of g of x is g prime x. So you just get the numbers in front of it. So you started out with this function af of x, you get af prime x. You started with bg of x, you get bg prime x. That's kind of nice, because now we could apply this formula here to sums or differences of different functions, as you would see later on, right? So I could say, you know, let's find, let me see. Let's look at our next example. Say you have 2x squared minus 3x plus 4. Say you have a quadratic, right? And I want to find a gradient. Let's try a simple value, -1. What's the gradient at -1? Well, we need to find the gradient function, okay? So we say let f of x be this thing here. Same strategy, right? F of x be that. And f prime x, we differentiate in y with respect to x. So you have to differentiate this instead of the 3x squared, the entire expression, right? So what would that be now? What would that be? We have three terms here, a 2x squared, a minus 3x, and a plus 4. Because the differential operator is linear, it distributes across addition and subtraction. So the derivative of three things is the separate derivatives of each thing. Okay? So let me write that here. How would we write that? Let me put it here. So you differentiate the 2x squared. Differentiate the 3x and your power minus in front of it. And then you differentiate the 4. Okay, so each of these things you differentiate separately. So the 2x squared differentiate at the -3x, you differentiate at the +4, you differentiate at. Let me put the -3 here and just put a positive sign here, but it doesn't make a difference, right? This rule up here says that the constants in front of a function, you could throw it outside the differential operator. So I could rewrite this line again. like this. And I could return the constant in front, I could throw it in front of the operator. So I could put it 2 here, take it out from here. I could put the -3 here, take it out from here. And the 4, I could just leave the 4, but if I follow the rule, 4 is 4 by 1. So 4 by 1, okay? So I could pull out the constants. 4 is 4 by 1, right? What is the derivative of x squared? What is the derivative of x squared? We use the rule here, right? Derivative of x squared is 2x. So this is 2 by 2x, right? So 2 multiplied by derivative of this, which is 2x, minus 3 by the derivative of x, which is 1, right? The derivative of x is 1 because the power is 1. So you get 1 in front by x to the power 0. Okay, I can even write it in here. 2x to the power 1, 1x to the power 0, right? We apply any rule, and plus 4. This is a tricky one now. Plus 4. Now 1, what is 1? 1 is really x to the power 0 if you think about it, right? But the derivative of a constant is 0. Okay, so this is 4 by 0. Okay, and it makes sense if you substitute if n is 0, that is a by 0 by x to the power -1. Anything by 0 is 0. And it makes sense too because you're asking what is the gradient function of a constant. A constant is a straight horizontal line that has no gradient, right? The graph of y equal 4 is a horizontal line passing through 4, y equals 4. No matter what x value it is, y is always 4. That's a horizontal line. That has no gradient. So geometrically, that gradient is 0, which makes sense. But when you apply the rule, you also get 0, okay? What is this now? This is 4x minus 3. That is what dy dx equals, okay? So we could put out here f prime x equals okay, so we find an f prime x, which is we differentiate it. So now the gradient function is 4x minus 3. So I want to know what is the gradient x at -1. So I have to find f prime of -1. Okay, so f prime of -1, you substitute that into the gradient function. -4, oops. And there you go, right? That's how you do a question like this. Given a function, what is the gradient at a point? If the function is a polynomial function, in this case, we had a quadratic, we differentiate each term separately. And that we could do that because the first differential operator is a linear operator. That's what the statement says here. The derivative of a sum of functions is the sum of derivatives. So you differentiate each term one by one, right? So I would differentiate with respect to x. That's what this ddx means. It means differentiate this thing with respect to x. If you differentiate a function with respect to x, you will get another function. That's what the differential operator is. It's a function that takes a function and gives you another function. Okay, differential operator operates on functions. So if I differentiate -3x with respect to x, I will get -3. if I differentiate a constant with respect to x, I will get 0 because a constant is not changing. It's constant. That's by very definition is constant, right? A constant doesn't change. So there is no change in y with change in x. That's why it's 0. Okay. Geometrically, it's supposed to make sense to you guys. So this is how you would do a question like this. And the textbook has some examples here how you differentiate certain things. You see, they have dy dx and they're applying the rule one time. I prefer this terminology here because it's very obvious that you're differentiating something with respect to x. Always write the d dx and in curly brackets put the function you differentiate. That's what I suggest because it's possible to get lost if you're just applying the rule here. Like is here, if you watch them here, they're just applying the rule here. Boom, one shot. What they're doing is differentiating 2/5 x cubed. Okay. It may not be obvious what it is happening here, but if you put the d dx of all of this here, the next line would make it obvious that this term here that is being differentiated. And this question here have 1, 2, 3, 4 terms. So it's 4 derivatives happening here, and then you just simplify it. Now, a point to note, right? This topic demands that your algebra skills with indices and factorization be on point. I don't know if you all realize that. Yeah, your knowledge of indices, your ability to deal with inverse fractions and exponents, factorizing as well. You need to be good at that because that's what's happening here. Okay. Let's deal with some more complicated functions. Well, still polynomials, right? Because that's the easiest class of functions in all of mathematics. If you find polynomials hard, then you probably don't want to do maths. It's probably not your calling, right? Because these are the easiest functions in mathematics. All the other functions harder than polynomials. Polynomials are very well behaved. How you deal with fractional indices. Find a gradient when x is 4. That's our example 3. 5 square root of x. Okay. So you're given a function y equals 5y square root of x. Find the gradient when x is 4. So I find the gradient function. Okay. So usual thing. Let f of x be the original function. So I'll write it here. So f of x is y, which is what I give you, is 5y square root of x. F prime x, which is dy dx, is found by differentiating with y with respect to x. So these first 3 things say you're always right. What are we differentiating with respect to x? Again, substitute this thing. Now, for polynomials to apply the rule is like this, right? Ax to the power n. So you have to write it as x to the power n. We don't have anything that looking like that here. So I want to rewrite it, okay? Five square root of x I want to write square root as x as something to the power n. What is that? That is x to the power. And is a fraction. That's x to the power half, right? So I'm differentiating 5 by x to the power half. I could pull the 5 out. Okay, that's the first thing. I could rewrite this and put the 5 on the outside. I'll take out this 5 here now. That's what that's Why? Because d dx is a linear operator. Constants in front of function don't take part in the gradient calculation, on any gradient function calculation. It's there, but you don't need to change up anything. So this 5 here, you can just throw it on the outside and just concentrate on this x to the half. What does the rule say? The rule says wherever the power is n, multiply everything by the power and then decrement the power by 1. So okay, let me write this here. So I will say 5 by, and d dx of x to the half, all this getting replaced. This getting replaced by, they say multiply by the power, which is a half. So multiply by a half, and then you'll get x to the power, which is 1 minus, I'll put brackets around it, 1 minus a half. Okay, and this could be, we'll put a bigger bracket here. Right? So 5 by a half by 1 minus, by x to the power 1 minus half. And I mean, yeah, kind of take your time and do this. Now it's just algebra. If you notice, differentiation done. It's just algebra now to simplify this. So this is 5 over 2. Take out the 5. And 1 minus 1 over 2. 1 is what fraction over 2? 1 is what over 2? That's 2 over 2. All right, so it's 5 over 2 x to the power 2 over 2 minus 1 over 2. This is, well, I mean, you could do that any other. 1 minus a half is just minus a half. Okay, x to the power negative half. And I don't need the brackets at this point. And x minus half, if I have to rewrite that without indices, that is 5 over 2 by square root x. I could take out his brackets now. So the gradient function, if y is 5 by square root of x, the gradient function is 5 over 2 square root of x. No, that's not really what I asked for. They say find the gradient at x equals 4. So they're asking you for f prime of 4. Okay. So let me try and get that. What is f prime of 4? Now it's just substitution really. F prime of 4 is 5 over square root of 4. 5 over 2 by square root of 4. This is square root of 4 is 2. We take the positive square root, right? So this 5 over 2, 2 by 2, yeah. That's 5/4. So if this is your function and x equals 4, the gradient is 5/4 at x equals 4. That this is it. This is how you write it. This is how you write the mathematics for it. You don't really write a lot of English. F of x, f is a function of x. Given x, we could find y. I don't want to know what the y value is. I want to know what the gradient is when x is 4. I could find what y is when x is 4. That's 5/2 is 10. Up here, I could find that. Just plug x equals 4 into the original function. I'll get the y value. I don't want the y value. I want to know what's the gradient when x is 4. So I need to find the gradient function. The gradient function is given by f prime of x. Another way of saying the gradient function is to say dy dx. If you know what y is, then dy dx is the gradient function. If you have f of x, the gradient function is f prime of x, okay? It's just two ways of saying the same thing. How do you find the gradient function? Well, you apply the first differential operator to the function itself. So you apply d dx to 5√x. You read this as, what is the derivative with respect to x of 5 square root of x? You pull out the 5 because it's a linear operator and you just apply the rule. You take the power half, you multiply by the function, and then you change the power by subtracting 1 from it. This is supposed to be a half minus 1 actually. Minus 1, right? So it's a half minus 1. And this is 1/2 minus 2/2. Right? So 1/2 minus 2/2, that's minus a half, and that's why you get that there. Okay. So it's a very simple differentiation question. Nothing fancy going on here. Okay. We found that the polynomial gradient function is the first gradient function formula that we learned, right? The book doesn't really give a proof of it, but it's given up here. We see differentiation on page 387. Y is ax to the power n. A is a constant, n is a constant. This is a typical polynomial function, right? X to some power, right? What we do is the coefficient in front of it doesn't really take part in the calculation, but it's there. It has to be there. What we do, we take the power, we multiply the entire function by the power, and then we decrement the power by 1. That is the rule we learned here. But there are other formulas to find gradient functions depending on the actual function itself. So they have sine and cosine functions, right? You see in blue here, we have derivative of sine or something. The sine function is a cosine, right? And the derivative of a cosine is a minus sine, okay? So if I have sine a theta plus alpha, the derivative with respect to theta, not x, is a cosine. Similarly, for cosine, the derivative is minus a sine. The arguments stay the same. Then you have exponential function and the natural logarithm function. This is the exponential function here. E to the x is a very peculiar function because the gradient at a point is the actual y value. And that's very useful, very, very useful function in advanced mathematics, right? What we call it the most important transcendental function in mathematics, e to the x, the natural exponential function. This function models the growth rate of a lot of things that occur in nature, okay? So the value of the gradient at a point is actually equal to the y value, this function e to the x. Is the only function in mathematics with that property, right? The gradient at a point is the value of the y coordinate at that point. Yeah. And we have these rules here, e to the x, a to the x is a to the x, and ln ax doesn't matter what's in front of the x, the derivative is 1 over x. And we could summarize that down here in popular gradient functions, right? A, n, and alpha are constants. This is the sine, this is the cosine, and this is the natural exponent, and this is the natural logarithm. These are the popular gradient functions. And the textbook shows how to find these things, right? I have some questions here. Find dy dx when x is 1. Give you an answer to, you know, certain number, significant places or decimal places, as the case may be, right? That's differentiation in a nutshell. You're basically applying the rules, but to solve problems is where coordinate geometry and so on comes in, right? So we see here ax to the n, sine ax, cos ax, e to the x, ln ax. We see here they're talking about the sum or difference, because it's a linear operator, it will be equal to a sum. So that's why when you have to differentiate, say 3 things here separated by plus or minus signs, you can just differentiate each thing one at a time and then combine them at the end, right? So that's kind of what they're hinting at here in these problems. But methods of differentiation tend to get a little bit more tricky, okay? We have differentiation of a product. We have something called the product rule, okay? We have differentiation of a quotient, something called the quotient rule. So you don't know that too. And then you have differentiation of a function, which we call the chain rule, right? So lots and lots of things to learn. Lots and lots of things to learn here. Making substitutions, doing it by eyesight, taking your time. Okay, it gets very involved, and this is what we'll talk about going forward. And then you might want to do differentiation several times. You might want to differentiate once, you might have to differentiate 2 or 3 times. Each time you differentiate, you have to apply the first differential operator again and again to get another gradient function, what we call the second derivative or the third derivative or the fourth derivative. That's what these things are. There's a fourth derivative with respect to x here. And these things have uses in engineering, okay? Which you will do when you start to do your engineering courses, right? But the techniques of differentiation is what we want to talk about next. And then we'll talk about the applications. This is where we actually solve problems in calculus, rate of change problems, right? So I urge you all to start reading these chapters here. We're really going to be specifically interested in maximum and minimum point, right? We are using integral calculus, we'll do integration after, but for differential calculus, we want minima and maxima, and that is where this section comes in, turning points. Yeah, you have to be comfortable with this section, how to find turning points on a curve, how to detect the kinds of turning points that I would have 3 kinds of turning points for normal functions, functions of one variable, and how to not only detect them, but say which one is which, because you have different kinds of turning points. So as you see here, chapter 44 is very, very important in addition to 42 and 43. So chapters to study, you see the differential calculus, 42, 43, 44, and 47. That's what I need you all to focus on. This is the next set of chapters to focus on, okay? The problems that you could solve with calculus tend to be geometric problems and rate of change problems. Any problem where some quantity is changing with respect to another quantity, and you want to minimize or maximize it, or try to find out what the combined rate of something is, you need calculus for non-trivial functions. Like you don't need it for quadratics, but for quartics and quintics and non-standard functions like x squared, e to the x, and x ln x, and these things, you can't really bluff with that. You have to use calculus for those things. And you see here, the tangents and normals come into play. There's more coordinate geometry here. What is a tangent? What is a normal? How do you determine these things? Small changes. All these things we have to do. 46 is the parametric stuff. No, 45 is the parametric. 46 is the implicit. We don't need to know how to do that. We're not going so advanced into calculus. But with the 47, you need to know the logarithmic differentiation. And when I come to do this, I'll teach you logs. I'm gonna use some logs for that. And that concludes the differential calculus, but we still need to go back and do some examples, so you can see some examples of how to do this thing, right? So what we have here, we have this exercise 152, differentiate with respect to x, these functions, right? So we could do some examples here. So if I give you this function here, 3 sine 4x minus 2 cos 5x. This is a combination, a linear combination of sine and cosine, okay? When I want to find dy dx, how you do this, right? Now you could just start off, you don't even need to say the let and all of that, right? You could just say, well, dy dx, and you just start differentiating, okay? So let me take out all of that here. Dy dx is derivative with respect to x of y, which is the derivative with respect to x of and the original function. So I put that inside the curly brackets here, right? So I need to differentiate this function here. Because the first differential operator is a linear operator, we could differentiate each of these terms separately and then combine them, okay? So what I want to do, apply the differential operator to each term. So the first one is that, and the second one is this. Okay, so I differentiated 3 sine 4x minus, because that was in front of the 2 cos, and then the derivative of the 2 cos 5x. Okay, so it's two things I'm doing here. So what's the derivative of 3 sine 4x? Well, the rule, the derivative of a sine is a cosine. And we know the number in front of the function, we could take it out. Right? So let me come to that, take it out, put it on the outside. I will put the 3 on the outside. And I'll put the 2 on the outside here. Because multiples of a function don't take part in the actual differentiation algorithm. We just leave them on the outside. They don't disappear, but they remain there. But they don't. We don't need to manipulate that number, the coefficient, right? What's the derivative of sine 4x? Sine ax is a cos ax. So whatever is in the brackets, we leave it, but we just, the number in front of the a, we put it outside. So d dx of sine 4x. I could replace this is 4 cosine 4x, right? So the derivative of 3 sine 4x, pull out the 3, and the derivative of sine 4x is 4 cos 4x, right? Let me, oops. So I pull out the 3 and I pull out the 2. Derivative of sine 3x is 4 cos 4x, sorry. The derivative of cosine 5x is minus 5 sine 5x. So this here, I could replace this. Minus 5 sine 5x, and just take out the ddx. See that? So the cosine, the derivative of cosine 5x is minus 5 sine 5x. And now we could simplify these quantities here a bit. So now we have 3 4s are 12, and minus 2 by minus 5 is plus 10. So 12 cos 4x and 10 sine 5x. That's the gradient function. That's what I ask you to find, the gradient function, okay? We have a function now with 2 terms in it. That is why, and we want to find the gradient function. And you know, you're gonna use the idea of derivative with respect to x of e to the ax is a e to the ax. And the derivative with respect to x of ln a of x is 1 over x. We kind of using that here. So they want you to find dy dx. What is dy dx? Dy dx is a gradient function. How do you get the gradient function? You differentiate the original function y with respect to x. And that's what the second set of symbols is saying. It means differentiate with respect to x, y. Right? Differentiate y with respect to x. See here? D means differentiate y, the function, with respect to x, right? Like that. That's what this middle term means. Differentiate the function y with respect to x. To do that, you have to apply the first differential operator to the original function. And I will give you a new function, which is a gradient function. What is the original function here? We need to put this in curly brackets because we are applying the first differential operator to these terms here. Now, because it's a linear operator, it splits it into the derivative of 2 things. So let me put that in now. So we differentiate the first thing with respect to x, which is 2e3x, plus differentiate the second term, which is minus 5 ln 4x, right? Differentiate these in respect to x. Because it's a linear operator as well, the number in front of the function, we could pull it on the outside. So I could rewrite this here. So I could pull out the 2 on the outside, take it up from here. And instead of the plus sign, minus 5. And then I could take that out. All right, so you see the minus 5 comes on the outside and the 2 comes on the outside. So I just have e to the 3x and ln 4x to worry about the algorithm, the actual algorithm that is. We need to apply the formulas for how you differentiate these things, right? The derivative of, sorry, this 2 is supposed to be here. Right, so the 2 comes outside, if minus 5 comes outside, right? The derivative of e3x is 3 e to the 3x. And the derivative of ln 4x is 1 over x. Right? So I could put this in brackets. Right? The derivative of ln ax is 1 over x. See it here? Derivative of ln ax is 1 over x. So that's 1 over it. Don't matter what that 4 is there, but the 5 comes along for the right. Similarly, 2 comes along for the right. What is the derivative of e to the 3x? E to the ax. You see here, e to the x is a e to the ax. So you take the a, which is 3, put it on the outside, and e to the 3x. What is this now? Let's simplify this a bit. This is 6 minus 5 over x. All right, so this is the gradient function here. 6e to the 3x minus 5 over x. We want to talk about some techniques of differentiation, okay? So we, first of all, how you differentiate products, right? To differentiate a product, we have something called the product rule. So the book actually goes into it in the methods of differentiation. See here, we have a product rule here, where the original function can be expressed as the product of 2 functions, right? So we could look at this simple one here. 3x squared sine 2x. U could be 3x squared, and if v is the sine 2x, okay? So u and v, you determine what your u and v are, and then you find your du dx and the dv dx, and you substitute it into this formula here, right? So it gets a little bit more complicated, obviously, because you don't really want to, yeah, it's not always possible to expand these things, right? It's not always possible to expand it because you have a trigonometric function by a polynomial. There's no expansion for that. Similarly, here you have a exponential, sorry, a polynomial as well, multiplied by a natural logarithm. So you can't really expand that out. This has to be a product. You have to treat it as a product. Okay. So that's how you would differentiate products. So we could do that. We could do that with a similar example. I will take an example here. Something similar to what they have here. What they have, x squared. So let's try. Let's try 2x cubed cosine 4x. Right? Yeah, let's try it. Find dy dx. There's a product. So the original function y is uv. Think of it as a product of two smaller functions, which are both functions of x, right? So y is uv. So if you apply the differential operator to a product, you have to use this formula here. So well, what is u and what is v? So in our solution, we will say dy dx is the derivative of y with respect to x, which is uv, where u is, and we'll say what u is 2x cubed, right? And v is cosine 4x, right? That's u and v. Now that we identify what u and v are, we need to find du dx and dv dx, okay? So what is du dx? Well, du dx is the derivative of u with respect to x, okay? We apply the differential operator to u. What is u? U is 2x cubed. And we know how this works. The constant can be taken out. So we could write 2 in front of this here, take it out here. And then we apply the exponential rule to that. What is the exponential rule? Well, the polynomial rule, right? Multiply the function by the power and then decrement the power by 1. So what is the power? 3. So this is 2 by 3 x to the power. And what is the power? 3 minus 1. Okay. So 2 3s are 6 x squared. 6x squared is the derivative of u. Du dx is that. And we could find dv dx as well. dv dx is the derivative of v with respect to x, which is the derivative of cosine 4x. Right? Now this, you can't take out any constant. They don't have a number in front of it, because we already took out the number for the x cube, but there's no number for the cosine. There's one number that we bundled up with x cube to make u. So there's no number here. So what's the derivative of cosine 4x? That is minus 4 sine 4x. Okay. Remember, the derivative of a cosine is a minus sign, and wherever the argument is in front of x, we throw it on the outside here. Now to substitute in the formula. So dy dx is y is uv, right? We said here y is uv, where u and that is v is that, right? So we substitute into this formula here. So we could say, type out that formula again. What is u? U by dv dx plus v by du dx, right? So it's four things we have to substitute here. So the first thing is u. U is 2x cubed. So 2x cubed as u. dv dx. What's dv dx? Minus 4 sine 4x. Minus 4 sine 4x. Okay. All right. What is v? V is cos 4x. And what is du dx? Du dx is 6x squared. All right, 6x squared. So then you multiply this now, and if you could factorize, you should factorize, right? So let's see this in action. This is 2 by 4, that's negative 8. Negative 8x cubed. So now I write that here, negative 8x cubed sine 4x, right? Plus, and I can write here, this is 6x squared cosine 4x. So actually, I could actually write that first. Always write the positive term first. Right? So 6x squared cosine 4x minus 8x cubed sine 4x. And you can factorize this. You could factorize this again. You always factorize your answers. Was it HCF for 6 and 8? So be 2 brackets. And 2 by 3 is 6. 2 by 4 is 8. And x squared. That's the HCF. So this x squared disappears from here, and the x cubed goes away to just give x. All right, so 2 by 3 is 6x squared, 2x squared by 4, 2 4s are 8x cubed, right? So that's the let me put curve brackets instead. Right? That's the answer for something like this. Okay. So the example was they give you a function and find dy dx. It's a little bit of work to find dy dx because you have to use the product rule because you have a product. You have two smaller functions which you have to differentiate separately and then combine them with the product rule. That's kind of what they're doing here in this example, problem 9. That's what they're doing. I just do it in more working for you for it to be obvious, right? They're taking kind of shortcuts here. Right? But that's how you deal with a product. Well, if you think products bad, quotients even worse, right? If you have to differentiate a quotient, u is always the numerator and v is always the denominator. once you establish that, there's a formula, which is a fraction here. V du dx minus u dv dx is in the numerator and v squared is in the denominator. That is actually the gradient function. Okay. Written another way, if you want to differentiate a fraction, a quotient, then if u is the numerator and v is the denominator, the new gradient function, well, the gradient function is this fraction here. So let's see what happens. Look at this example here. 3 cosine 4x over 5x squared. Find dy dx. So I mean, take your time. Dy dx is the derivative of y. Y is u over v, where u is what? 3 cosine 4x and v is 5x squared. So again, we have to find du dx and dv dx. Okay. I'll do some work here. So let's steal this and see how far I could get with it. All right. Could put this one here. So du dx is the derivative of u with respect to x, which is the derivative of 3 cosine 4x with respect to x. As we know, because it's a linear operator, we could take out a 3 and just deal with the cosine 4x. This is 3 by derivative of a cosine is a minus sign, minus 4 sine 4x. Minus 12. Okay. So that's your du dx, that's your numerator, right? Minus 12 sine 4x. The denominator now is the dv dx. That's the derivative of v with respect to x. V is 5x squared. We could pull out the 5 and just deal with x squared. And this is 5 by 2x. Not so bad. That's 10x. That's the denominator derivative, right? 10x is the answer. So now I have this formula here. Let us substitute now. So dy dx is derivative of a fraction, which is that. Now we have to plug all of these things into this formula. So I'll take your time. So let's write a fraction and put dy dx equal to that. Right? So we want to substitute for v. So the numerator really is something. Let's write it out. Something by something minus something by something all over something squared. All right. So I set it up. There's 2 things minus 2 other things all over something squared. So we want to substitute, right? What is v? V is 5x squared. So we substitute in for v, right? So I have 5x squared and 5x squared. All right, that's v. V is the first thing and the bottom thing all squared, right? What's du dx? Du dx minus 12 sine 4x. Substitute that for du dx. What is u? U is 3 cosine 4x. Let's take this here, substitute it here, u. And what is dv dx? dv dx is 10x. All right, substitute in this side here now. Wow, okay. So it's a long expression here. What we need to do now is multiply this out and simplify. All right, so this is 5 by 12. 12 have a 3 in it, and have a 3 here. Another 5 and 10 have a 5 in it, right? So we write it, let's rewrite it out. The sine 4x, we're really gonna get minus 60, all right? 5 by 12, 60, the minus sign, the x squared and the sine 4x. 3 by 10 is 30, so we have minus 30 here, x. Right, minus 10, 3 is a 30x cosine 4x. On the bottom here, this is 5 5s are 25. And x squared squared is x to the power 4. Right? Could factorize some of these fellows here. Let's see. I could pull out a minus 30x. So I could write minus 30x square brackets 2. Put a closing square brackets here, yes. If I take out 30, if I take out negative 30x, here would be 1, but here would be 2x. Right? X by x is x squared, 30 by 2 is minus 60, minus 30x by 1 is minus 30x. Okay, good. I see the 30 and the 25 can cancel too. So again, it's wise to take your time and do that cancellation after. 5 into 36, 5 into 25, 5. So this negative 30 becomes 6, and this becomes 5x cubed. Right? 5 into 25, 5. This x up here, oops, I did. Forgot. All right, so negative 30 by 2 is 60x squared, and negative 30 by 1, negative 30, right, 25. 5 into 30 is 6, 5 into 25, 5. This x up here cancels with this x down here to give it x cubed, and this is the derivative. As you see, it's a good bit of work to deal with a quotient. And it's kind of like what it did here, right? Look how much work in they have. They have a lot of work in for this question here. And they represent it as a fraction. You will get a fraction in effect, right? You can write it like this or like this, right? that's for a quotient. And you see here they try to do it with tan x. They represent tan as sine over cosine, and they get some operator called sec squared, which is 1 over cosine squared, right? So you could do a lot of stuff happening here. Watch out this question. This is a question to give you stress here. Find a gradient at that point. You see how they give you SIDS? They give you SIDS here at this point. So you have to substitute that into this equation here to find a gradient, right? And we have further problems. Now let's talk about differentiating a function of a function. Probably one of the most useful theorems in differentiation is what we call the chain rule. Right? This is you'll see it some places called the chain rule, and the chain could be any size long. Here the length of it is 2. Is 2 elements in a chain. But the size of the chain could be arbitrarily long, right? Because we could always define functions in terms of functions, right? For mathematics, we have function composition, right? So if y is a function of u and u is a function of x, then dy dx is dy du by du dx. You could think of it as the du's canceling to give dy dx here. But again, this is not a fraction. This is a function notation. Du dx is not a fraction. It's a symbol. It's a symbol that names the gradient function of u with respect to x. That's what du dx is. It's not a fraction. But if you want to remember the formula easy, you could think of it as a fraction, and these du's canceling here to give dy dx, right? It really is the product of two smaller gradient functions. So I'll illustrate with an example. If you had to find the dy dx of cosine cube of 2x, that's really cosine 2x all cubed, right? So you say let u equals cosine 2x. So then y is u cubed, right? If you cube the cosine of 2x, you'll get cos cube 2x, right? So again, you find dy du and du dx. So let's try and do that now. Dy du is what? That is negative 2 sine 2x. What we're doing is we differentiating u with respect to x, right? Du dx. So u is a function of x. Dx. We differentiate this here with respect to x. Differential of a cosine is a minus sign, and we get negative 2. We need to find dy du, because that's the formula, yeah. Dy du. So if y is u cubed, what is the derivative of y with respect to u? With respect to u, that is 3u squared. We use the polynomial rule, right, from before. Dy du, you differentiate and u cubed with respect to u. So I could probably write that. So dy du is you apply the differential operator with respect to u for y. You apply it to y. And well, that is equal to differential operator applied to u cubed. So, you know, it'll always have to be with respect to x. If you differentiate in u cubed with respect to u, is the same as differentiating x cubed with respect to x. The variable you're using is not really important. It's the differential with respect to that variable. So I get 3u squared. Now we need to apply this formula here. So dy dx dy du by du dx. So there's two things being multiplied, just like before, right? What's the two things? The dy du, which is what? Dy du is 3u squared. So multiply the 3u squared. And what is the du dx? Minus 2 sine 2x, right? Okay, cool. Let's simplify this thing. So what is u squared? Well, we have a substitute for u. U is cosine 2x. So this u squared is really cosine 2x all squared. So I could put a square bracket on it. There's the cosine being squared, right? So the only thing that changes is a substitute for u. What is u? U is cosine 2x. So you see I have the cosine 2x all squared here. So let's deal with the other parts around it. Take our time and simplify this. Yeah. So 3 by 2 is negative 6, right? So let me write negative 6. Take out the times. Right, so the 3 by 2 and the negative, that's negative 6. You see cosine 2x all squared, you write that as cos squared 2x, and then you're multiplying by sine 2x. So this is the derivative of that. And you could use identities to express it in terms of sine alone or cosine alone. But it might be easier to do in terms of sine. 1 sine squared plus cos squared is 1. Right? Those are some identities, simple identities from C-set maths. So the chain rule is what you would use when you have a function of a function. And then the trick now is to determine when you watch a question, what the hell is this? Is this a product? Is this a quotient? Is this a chain rule? We'll talk about successive differentiation when we start to do the applications of differentiation next class, right? But I urge you to read the chapters, right? I urge you to read these chapters here for differential calculus and go through the questions and make sure you understand the solutions. Because this is heavily intertwined to coordinate geometry. When you have a gradient of a tangent line to a curve at a point, cutting the x and y axis, or maybe the midpoint of a line with the perpendicular bisector, the point cutting it with a curve, and you could get real crazy with these things. Coordinate geometry, I did it in lecture 9, right? We did a lot of the basics in lecture 9. And these questions I gave you all to do, and I hope you're all able to figure it out. But it's gonna get more serious than this as we add calculus to the mix, because we have to find minima and maxima, and these are geometric problems. These are problems with that you could see when you sketch a curve. Was the minimum value of a function, was the maximum value of a function within a certain region, right? As what minimum and maximum is. So this is very much related to coordinate geometry, this stuff and this stuff as well. All these things here, areas under curves and things, very much related to coordinate geometry, right? So how you would know when you look at a question. Like if you look at these exercise 157, how you know what is a product, what is a quotient, what is a function of a function? Like what is this here? Is this a product? Well, when you see in cosine, right? So it's not a product, it's not a quotient, but it's something to the power 5. We just did something to the power cubed, right? So there's probably a function of a function, yeah. If you get a miscellaneous quiz with all kind of things happening. Look at these problems here where you have to differentiate 2 times to get a differential equation. See, it's a lot of work. These questions are a lot of work, and they demand a strong background in algebra. This is why calculus is scary. You have to know all your algebra, all your quadratics, all your factorizing, all your surds, simplification, expanding, all your indices, right? There's a lot of stuff you have to know before you do calculus, which is why calculus is typically taught after you do 2 to 3 years serious mathematics, right? Mainly algebra and the trigonometry. Very, very important before you start calculus. That's why we did so much lectures, right? We did all these lectures here up to 9 was just algebra. And people will be saying, this man only teaching me one topic, algebra, like, yeah, nothing else. That's because this is the 3 years algebra you have to do before you start calculus. I just do it fast in a 2 months or 2-3 months, if so much, right? So yeah, we have methods of differentiation. We have the product rule. Where is it? Product rule here. We have the quotient rule. We have the chain rule. And we know how to differentiate simple things. Polynomial, sine, cosine, exponential, natural logarithm. It's supposed to be /ln. Yeah, /ln. Ln. Ln is a natural logarithm. For those of you all who don't understand logarithms, I'll probably do a review next class, but there is a chapter in the textbook on logarithms. It's probably one of these chapters up here in the algebra foundations. Is one of these chapters here show for logs. What is a logarithm? Somebody asked the question, what is ln x? That is the natural logarithm of x. Where did it go? See it here? Look how ln x looks. This is natural logarithm, ln x. This is a logarithm function where the base is the natural number. E is the natural number. The second most important transcendental number in mathematics. The most important number, transcendental number in mathematics, of course, being pi. Right? So there you go. That's it for the lecture today. We did the notation for differential calculus, what the differential operator is, what the gradient function is, how to find the gradient function of common functions, polynomial, sine, cosine, exponential, logs, is a linear operator, so it distributes across addition and subtraction. And when you have a number in front of the function, a coefficient, you just pull out the number on the outside. Right? We learn techniques, products, quotients, and functional function. Out of all of these here, you see the product and the quotient. This is the most important one here. See function of a function, this chain, right? This is really the most important. Then these actually come into play. It have certain things you cannot differentiate without product rule or quotient rule. That's just how it is, right? So, hope you had fun.